having enough pairs, we can solve for alpha. We can solve for alpha I. Okay? We can solve. All right. And then we are done, because now we can invert any if you want to invert compute the image of any of any value. Now we know that, and we want to know the preimage of any y. We put here y. We know y, and then this is a linear equation with the unknowns are the x. So you see really how it works. The first attack I told you is the relinearization attack. But this is very special for this kind of map. Okay, I say this map is not affected by Grosvenor basis attack, but this has this fatal property that really kill the system. Okay, so you see how it works. All right. So it's a nice example. Okay, then I will explain. The system that that after the next system that is the base of most of the multivariable encryption system that we have is called the HFE. It was there was also by Patahan. So this is French, so it's pronounced Patahan. HFE, I mean hidden field equation. Hidden. In this case, we took our central map is more or less the same setting. So I don't know. So we'll have Q P to the A, okay, and then we have an isomorphism between F Q N and F the big field Qn. All right, and then the central map is. The central map is, in this case, is f of z is equal to the sum of alpha I. I mean, it's not the same. We call it beta ig z qi plus qg. And here we need qi. I will explain why. Plus qg is less than or equal to d. Okay, we have to, this usually should be a small. All right, so after, so we have the same, so now this map is not anymore injective, but can be inverted. So how to encrypt? Okay, how to decrypt? To decrypt. Decryption, so the map is clear. So we have, as always, P of y, of x equal to y. Okay, so I didn't remember the P is the composition of phi, the linear isomorphism after and before. Okay, I did not write. So how to invert? So again, we have to invert the central map. We have to invert the central map Z F. Okay, so we have so we have here. Then we have to compute, if you like, solution of this map. I will put like that. This minus y equal to 0. Okay, right? for y in the big field. All right? Okay, and then this is just, this is a polynomial in one variable, so it's just how to, this is how to find the root, so we have to find a root of this polynomial, okay? I will call this of star. Of this univariate polynomial of star, that, remember, is an univariate polynomial. Okay, and then how is done? There are, I mean, over finite fields, there are many algorithms to do that. In fact, what the algorithm that we use is the algorithm to factor this polynomial. So they are in computer algebra, the main algorithm for factoring one polynomial in one variable are, for instance, the Bernstein's polynomial, right? Bernstein algorithm, Cantor-Tassenhaus. Algorithm, factorization. So this is very well known, very well explained. It can do, but the complexity is of the order of something the degree to the cube. Okay, so this is the complexity of computing the root of this polynomial. Okay, and then. And of course, because we know that this, because they come from encryption. Encryption gives you one value, and one value here I found the polynomial. So we know a priori that it has a root. So that means that we will find at least a factor of degree 1. Okay, so that's so this is the complexity, and that means that. This has to be small. Small means, I don't know, 200 has to be small. Small for the size, something like maybe 200 or 250 or whatever. So this is what means small. Remember that we are in this field. We are something usually the q has to be q to the n will be of the order of 2 to the 128. So this is really related with the possible degrees of the polynomial is very small. Okay, all right, and okay. Now, this really has been the basic for all, but this again can be, this in fact can be attacked using Grotner basis. All right. So you know here when we pass from here to remember to the P1 of x, P1 of x. This remember this make, because we use generic linear. This looks very this map looks generic. Generic dense polynomial. Okay, but so in principle it will be very difficult to compute even Grotner base. I mean, for a generic dense polynomial, the Grotner base cannot be computed. I mean, the complexity is with this size, complexity is completely impossible. But this comes, in fact, one of the now we can make propaganda of Grotner bases. This really comes one of the mysterious things of the Grotner basis. Is that Grotner basis can distinguish between a system of polynomial generic and another coming from, for instance, from this one, that they are not generic, but they are really look generic. They are completely dense. So this is a completely, no one can explain why you know, but I don't know. No one can explain why Grosvenor bases can distinguish between two systems that looks exactly the same, but one is the same in the sense that they are completely dense and random, but one is easy to compute and the other no. So this is really, so in fact, so you think to attack, so here come. So attack, as I say, now we can use Grosvenor-based attack. Grosvenor-based attack. Attack in the sense, of course, we can always, as I say, we can use Grosvenor-based, but attack means that this lower the complexity, really is effective, okay? And in fact, this was, for several years, there was, I mean, people tried to attack, but finally there was, using the magma system, I will maybe, I'm sorry I don't use, I know singular, but I use magma computer algebra system. Maybe I will show you. That has the best, I'm sorry about my comment, but it has the best, maybe you don't agree, the best Grosvenor basis algorithm for finite fields. I mean, it has implemented the F4 and F5, F4 at least. I mean, but the implementation is really very good. And in fact, it broke after several years, broke a system with Q. Broke a system HFE with, I think, Q equal to 2, N equal to 80, something like that. Well, probably you remember. There was a big hype about that. So really, as I say, really, Grosvenor base can distinguish between the two things that looks in the stereo equal, but it has something high in interior. So really, this is, for me, I never, always make propaganda on Grosvenor bases. This is in the sense that it's completely mysterious. Do you agree with that? Of course. All right. Then, so this is an example of the, and in fact, there was many variants, but I will not now because before that many variants. Many variants of HFA, many. I mean, it has been a study for 20 years, no? But at the end, the conclusion is that, I mean, it's not safe for, in general, it is considered not safe for encryption, but it can be safe for signature, okay? For instance, for the many variants, for instance, I will explain two of the more important is we can one variant is what we call HFA minus, is that when you have FQ to the n and FQ to the n, okay, and then minus means just you erase, you have P1, PR, and just you erase some of the Pn, you take out some of the and that means that we will get here, okay, and then and this can be used, and you keep this secret, and then as I say, this can be used for signature. Signature you don't need, do not need to be injective. Okay, you only need to invert, and you can invert even you keep this secret. You give generic any value, so that means that you will find many signatures. But this is not a problem as far as you can. It's difficult to get to have many signatures is not a problem. Okay, as far as it's difficult to get to invert. And the other variant, important, there are many, the other family of variants, I mean, there are more, but these are the most important, is just to add generic, several generic means with random coefficient, generic quadratic map. And then you will have, in this case, will be from FQ to the N to the FQ to the N plus, I don't know, plus M, okay? And then this keeps injective, all right? So again, it has give more security, but I will there are many more variants, but I will not continue with that. Then as I say, we have three kind of attacks. I will go with the last one is the mean rank attack. Okay, so the mean rank attack is remember that you have F. Okay, remember P, the central map, and P are quadratic. P of X are quadratic, is are quadratic. That means that this is P1, Pn, where Pi is quadratic. I mean quadratic, degree 2, okay, degree 2. And then that means that it can be expressed in a matrix form. So we can put Pi, Pj, we can express in the form S1 xn for a matrix Qj, S1 Sn. Okay, and then this is a good example because of the structure of the way that is the central map. These quadratic forms, I will not give the details, but this quadratic map can be extended to FQ to the N. You know, sometimes when you have a problem, you put it, make it even more difficult. You just studying the question, not in the original field, but in the big field. Okay, and then things become easier. So, okay, and so you can, and then because of dexterous, the rank of the matrices the matrix is low. Or you say unexpectedly low. I mean, is low. Really, unexpectedly, we'll say it's low. I mean, all right. Okay. So that's and this cannot be hide. And this fact that the rank is low, I will not. I have no time to explain why is this, but this cannot be hide using, and this fact cannot be hide by the masking system that we have, with the help help of the linear isomorphism, T and S, the linear. So this is also a good example of what we...
So you have time till 40.
Okay, all right.
So you have
Yes, yes. All right. So this is a good example. Also, what we explained yesterday at the beginning, that we this kind of way to get public key cryptography has some danger. I mean, we really have a NP complete problem. I mean, we have an NP complete problem, but you choose an easy instance of this NP complete problem, but it's really very difficult to hide that this is an easy example. So this is a very good example of this strategy, because now the problem is how we can attack this using the mean run problem. What is the mean run problem? The mean run problem is the main problem is the next one. Take I don't know M1 MK matrices in matrices M times n over a finite field FQ, right? And find a linear combination you say lambda 1 with coefficient lambda 1, lambda n, such that lambda 1 F1 rank of lambda 1 M1 plus lambda n Mn is low, is equal or less or equal A R, and R is low. No, this is a problem that appears in many instances, but this will be a case in which mean rank this is a case of mean rank. You know, we have this quadratic polynomial that can be expressed in matrix form, and then, but we know that we have a linear combination of them who has low degree. In fact, in this case, the low rank. The rank, it has to do something like log Q of d minus 1 integral part, something like that. Okay, log Q.